exponential functions and their graphs. Okay, so here's today. We are starting 6.1. Exponential functions and their graphs. Okay. Let A be a fixed, positive, real number not equal to 1. Okay. And then you have the exponential function where they say f of x equals a of x. Okay, this function is not to be confused with some of the other ones you've seen, okay? This is not x cubed or x squared or so on and so forth, okay? It is not one of them, okay? Because notice on those, it's the x value that changes, but the exponent stays the same. You're noticing that, okay, obviously, but people do tend to confuse those just a little bit, okay? This one, your base will always be that whatever A is, okay? But X is now going to become your independent variable that changes, okay? Also, just so you know, okay, your base cannot be a negative number, okay? And there's a reason for that. If you go all the way back in time, it's going to make sense to you that if I give you something like this, say I give you the example of -2 to the 1/2 exponent. Well, realize what you're actually seeing there is actually the square root of -2. Okay. And so therefore, it's not a real number. And look at how these are talked about. Let A be a fixed positive real number. That's not going to end up being a real graphable number right here. Okay, so that's come. All your A's will always be greater than or equal to 0. No, sorry. 0 wouldn't matter, but still greater than 0, positive. Okay, so stick with the definition. Ignore that greater than part or equal to part. I want you to note something. The y-intercept of an exponential function, y-intercept, okay, is always the point 0, 1. Okay, let's remember, for it to be a y-intercept, what are we making a 0?
X.
X. Well, what happens if you have a 0? What is anything when it has a 0 for an exponent? Think about it. It's always a 1. Okay, always. Anything raised to the 0th power is 1, except, you won't run into this very often, 0. 0 raised to the 0th power, sounds stupid just hearing that, is undefined. Okay, but you won't have to deal with that. Okay, just letting you know that now. But that should be, kind of put that in the back of your mind. But everything raised, if I put a 0 here, everything's going to be 1. Everything, doesn't matter what it is. Okay, if I raise it to the 0th power, it is going to be 1. Okay, these functions, not that you really need to know this, but you will hear the word. The function we're going to be dealing with there called transcendental. Okay, notice exponential functions are the first examples in this course of transcendental functions. So because of their definitions, transcend, okay, or go beyond algebraic operations, okay, which means some of the things you're going to be doing are going to be like you've never done it before. Doesn't mean it's going to be bad. You're still going to be doing plus, minus, all that kind of stuff. It's just they're going to look differently, okay, to deal with these. The formal definition of transcendental function is a function that does not satisfy a specific type of polynomial equation, while an algebraic function does. Polynomial functions, root functions, and rational functions are all examples of algebraic functions, while logarithmic, trigonometric, and hyperbolic functions are further examples of transcendental functions. You will be learning these in this class, obviously. Okay, the logarithmics. Then you take trig, learn trigonometric, and then hyperbolics happen a lot later. Master's level math classes, maybe upper division, not even master's level, like junior, senior level math classes. And even then, didn't happen very often. Like I didn't deal with hyperbolic functions until my master's level in math. I never dealt with them any other time. I deal with them a lot in physics. If you're into you future physics majors, you deal with hyperbolic functions a lot. Okay. Other than that, that's just definition for definition's sake. So let me show you what they look like. Let me show you, give you two examples here. Notice I can create a little table here. Okay. Both of them f of x, one of them less than between 0 and 1, and one of them greater than 1. Notice the base. Okay. On one base, I have 1/3. On the other base, I have 2. Okay. Notice what's happening with the value. Okay. When it's less than 1, but greater than 0. As x gets what? Large. Okay. What is happening to my other number? Huh? Getting smaller, isn't it? Okay. Whereas if my x is greater than 1, okay. 1, we don't ever use 1. That's like I'm saying not equal to 1. If you put 1 in for the base, well, let's be honest. 1 raised to the power of 1 is just what? 1. You get a straight line. Okay. So that's like when we always say greater than 1 or less than 1. Okay. So we would call it a constant. So, but notice here with the 2 of x, as x gets large again, what's happening to the y value? Itself is getting large. Okay. The reason I say this is because when you start graphing these, it's going to be a lot easier to just go and do some test points, just to kind of have an idea of what they're doing. Unless something has been flipped, because a lot of your rules that you learned about graphing still apply. Okay. If you have a negative base, it's going to flip across the x-axis. Okay. Stuff like that. Okay. So just kind of remember that. It still works exactly the same way. If you have a +1 sitting outside of it, well, you're just going to take that guy and move him up 1 or move him down by 1. Okay. Let's look at the graphs. Here's an exponential graph. Notice this first one here is at 1/3. This means 0 for that x value, my exponent, is between 0 and 1. Can't equal 1, can't equal 0. If you equal 0, you don't have anything. And remember, you can't raise, it's undefined also if you accidentally have a exponent to the 0 power. But look what's happening to it. It starts way up here and goes that way. It kind of looks like a weird slide, right? We would call this one on the left-hand side, we would call this a decreasing function. And while it may not look it, this decreasing function here, this f of x, as f of x approaches infinity, x goes to negative infinity. As f of x approaches 0, x approaches infinity. Remember f of x, that's your x value, right? As x goes this direction, okay? As x goes to negative infinity, what's happening to your y value? It's going to go to infinity. There is not an asymptote here. Okay? Exponentials, going to sound redundant how I say this, but exponentials grow exponentially. They grow really, really, really quick. Okay? Like it doesn't take them long before they're off the chart. I mean, notice you've got right here where x would equal 1, right? Here is where x would equal 3. But notice x would equal 2, -2, like way up here somewhere. -3 is going to be just that much higher. Okay? But it's going to keep going. So that's why your domain here, while it's really hard to tell because of the graph, the domain is still all real numbers. Okay? Because while it looks like it curves up, it's going to get to negative infinity. It's just going to take it a really long quote unquote time to get there, but it has an infinite amount of time. So it will get there. That may kind of make sense in a very weird mathematical, non-mathematical way. Your range would be from where? 0 to where? Infinity. Okay. This, notice what's happening here. As x approaches 0, as it's getting closer and closer to that 0 line, it will never touch it. Ever. Okay, it can't. It will approach infinity. But your values are going to get infinitely small. Okay. Same thing over here. Notice over here you have anything greater of x is greater than 1. I do want you to realize, look at the y-intercept of both of them. The y-intercept of both of these, no matter what, is what? 1, right? Because anything raised to the 0th power, because x is 0 here, that's how you find your y-intercept. Anything raised to the 0th power is always 1. That's how come your y-intercept for the base graph is always 0, 1. Okay? Notice on this one, once again, you have a domain of all real numbers. You would also still have the same range of 0 to infinity again. But notice how things have changed on this one. When you have f of x, okay, as f of x approaches infinity, x approaches infinity. As f of x approaches 0, x approaches negative infinity. Okay. And that's about all she wrote on these. Okay. I do want you, and I'm going to show you some examples how we're going to work out some of these. But right now we're just worried about the graphs. Okay. Graphing in your homework is going to look like this. It's going to say, hey, pick out the graph. Okay, that makes it easy. On your final, it's not going to be that way. Okay. I suggest now learning how to put in some test points. Okay. If you can find some test points, it's going to make it just super simple. You only need about 3, and you've got it. Okay. Most of your test points, okay, what they suggest, and I agree with them, I'm going to give you the numbers. Always use these. I'm going to say always. I don't like that word. I don't like that. It's helpful to use these 3 test points. -1, 0, and 1. If you can see what the graph is doing at -1, at 0, and 1, you're pretty much going to have an idea of what it's doing at that point, okay? The reason I say that is, remember, these guys get really small really quick or really large really quick. So if you try to pick out a test point outside of that range, even at 2, if I gave you like a to the, say, 3 to the power of 10, okay, and you are 3x, and you put in a 10 in there, bro, that's 3 to the 10th power. That's going to be your value that you're going to have to try to, that's not going to work. So you notice how keeping it small makes it a lot easier, okay? And you can even use decimals if you want, okay? But I am just saying right now, -1, 0, and 1, keep it easy on yourself, okay? So let's look at 1. And here we have it right here. It says, 1, indicate which of the following 4 graphs is the correct graph of this function. First off, what I do want to help you with is look at this. Anything where your base, the A, okay, are you listening to me? The A value is between 0 and 1. You have one that's a decreasing function, okay? If it's larger than 1, you have an increasing function. Now, do not get fooled by fractions. That is not a small fraction, is it? Is it a small fraction? No. Is that between 0 and 1? No. You're actually seeing what? 2.5. Okay? So knowing that, here we are. I can at least say this. Hey, I know it's not that one. Because that's a decreasing function. That's only going to look that way if it's going to be between 0 and 1. But now you've got to start going, okay, which is on the other ones? Okay. Well, notice the x value hasn't been moved at all. Okay. Has it? Look at it. Do you see a +1? No. Do you see a negative sitting out front? No. So as I've stated before, since this is a base graph, okay, base function, what is always going to be the y-intercept? Yeah. Look right here. 0, 1 on them. Okay. Now, it does not mean that it can't be moved. That's what happened here. This one you would have saw like an x plus. Okay, remember? Because that's when, sorry, an x minus, because that's when things get moved to the right. The other one there, well, notice what happened to it. It actually got moved down by 1. But there's no x, there's no -1 sitting out here somewhere that would have translated that down, did it? No. So we can just say, hey, that's my guy right there. Or what you could have done as well, come in here very easily, and then you've got f of x, and literally you'd come here, -1, 0, and 1. I know at 0, I've got to have a 1. Just in case, shouldn't you put that into your function, right? Okay. I'll give you the other two. When you do this, you end up getting 2 over 5. And also 5 over 2. And there you have it. You could go in there and graph those. It'd be tough, but there you go. You have some test points to play with, right? With just those 3, you can go, oh, there it is. I found it. That's what you're going to have to do probably on your final, or do what I just did. You go through that process of elimination. Okay, is my A, is it between 0 and 1? If it is, it's going to look like this. Now, what's happening after that? Is there a negative? Okay, that means I flip it. Is there a +1 with that x? Okay, that means I'm moving it left or right, or a -1. Outside the function, is there a +1? I'm moving it up or down. Okay, notice these translation rules are still the same. Okay. You give graphing? Okay. Indicate which of the following graphs is the correct function for this one. Now look at this one. First off, am I going to have an increasing or a decreasing function? Increasing. Since I know it's increasing, I can come in here and go, okay, well, it's increasing. That means I know this one doesn't work. Looking at it carefully, before I look at the x value, would you say this graph is going to get moved up or down at all? Down. Think about it. Go back in time to how you translated graphs. Is what's happening to the explicit base function, or is it sitting outside of it? Think about it. Do you see a plus or -1 sitting over here somewhere? Or plus or minus any number? No. Since that's not happening here, you're not going to have an up or down movement. Okay? But notice that explicit x value. Go back in time. Like say I showed you 1 over x squared, and I said 1 over x squared minus 1. Well, notice something's happening to that x squared. We're going to have to go left or right now. This one now, I showed you 1 over x squared plus 1 sitting out here. That's when it went up or down. Well, that's not happening here. So now this one right here is going to go where? Left or right?
Right?
Right, because you see a what value?
Negative?
A -1. Okay, well, let's think about it. Our y-intercept is always what? 0, 1. Well, let's look at all of these. Shouldn't it have been right here? But if I moved over by 1, where is it at now? Right there. So that is my graph. Because notice all these other ones. Here, on this one up here, you can see it went over 1, 2. Well, that's too far. Over here, look what happened. It went up 1, 2, 3, and it went over by 1. Well, that doesn't work either, does it? Okay. So notice by knowing our y-intercept is 1 always at its base level. A to the x is going to have 1 as its y-intercept. We can start playing with it from there. So you start translating these things, translate it from the base graph first, and then start doing all your movements. Once again, even in your notes, I do the math. I show you -1, 0, and 1. Okay. We won't worry about that right now, though. All right. Solving. There you go. That's some algebra, did you? To solve an elementary, they say elementary because you'll see why whenever we get to 6.3. An elementary exponential equation, perform the following steps. Isolate the exponential, move the exponential containing x to one side of the equation, and any constants or other variables in the expression to the other side. Simplify if necessary. Find a base that can be used to rewrite both sides of the equation. Equate the powers, solve the resulting equation. What I have found that the hardest part about this one is this. You've got to create the same bases. In 6.1, you're going to be able to do that every single time, I promise you. Okay? So email me if you need help, but I promise you, there's a base out there you're going to be able to change all these into so your bases match always. Okay? It's just not always going to be plain and simple. You also got to be careful. Sometimes your base, to get it matching, you may have to use a negative exponent. Remember, because what that does, you get a fraction, that's going to flip it. Everything on the bottom is going to go to the top. Everything on the top is going to go to the bottom. Okay, so kind of just be ready for that. Let me show you what this means by example. With this guy right here. Solve the following elementary exponential equations. 25x minus 125 equals 0. You're literally solving for x. Okay. Well, let me show you how this is done. First off, it says isolate the variable on one side. Isn't that what we've always done? We have a variable x. We need to isolate that base with the variable on one side. So I'm going to add 125 to both sides. Okay. And I'm going to get 25x is equal to 125. Now notice, you need to make sure that you have the same bases. Okay. And unfortunately, by this, what it means is you're going to find some base to some power and make sure these guys match. The bases are going to match, the powers are not. Okay? Watch what's going to happen here. So hopefully you kind of get the example. 25x, if I go back down to it, can I not rewrite that as 5 squared? 5 times 5 is what? 25, exactly. Now realize how I'm about to write this. I'm going to put this whole thing, the whole thing in a parenthesis, and then put this x right there. What could how could I rewrite that 125?
5 cubed.
5 what?
Cubed.
Exactly. Notice that's 5 cubed. I don't have any other power there that I don't need to worry about. Now, if there was a power out there, put it in parentheses, okay? And put that other power on the outside of the parentheses. Now notice what's going to happen here. I'm going to take that 2 and multiply to that x. Okay. Well, now I'm going to make the powers equal to each other. So I'll come over here and notice what I get. 2x is equal to 3. Solve for x. X is equal to 3 over 2. That's the exponent I was looking for to make that statement true. Can you check yourself? Yeah. You can come in here and go, okay, I've got 25. Isn't that really what you're saying there? When you see 3 over 2 minus 125, is that equal to 0? Well, 25 cubed is going to be a very large number, which I can't tell you what it is right now. But I will tell you this. When you take the square root of it, guess what you get? 125. 125 minus 125, does that give me a 0? There you go. And you can also check in your calculator too. Just throw it in your calculator real fast, see if it works. Okay? But that's how that works. That's how you're going to solve these exponentials. Okay? Like I said, this is elementary solving. Okay? This only works, this method, right now, whenever I can find two bases that are the same. Okay? And there's some other little quantifiers. So having said that, showed you that one, let's see if you can work with this one. Don't overthink it. Do the exact same thing I just did. And then I'm going to work it. You're working this, I'm going to give you a hint. It's already in the proper form. You got a constant on the other side. You're good. You don't got to move anything around. Okay. You can't move the exponents around. You can't get them around. They go with the base. Okay. You know what I can change that 27 into?
3 cubed.
Very good. 3 cubed. Don't forget to put parentheses around it. Three cubed, or sorry, 3 times -3 is just going to give me what?
-9.
-9. So notice all I do here is go x squared plus 6x is equal to -9. Well, you're dealing with a quadratic, so you're going to make it equal to 0. X squared plus 6x plus 9 all equal to 0. Very quickly, I'll factor that guy. I've got an x in both, a plus in both. And how about a 3 in both? 3 times 3 does give me 9. 3 plus 3 gives me 6. I know that thing is factored correctly. So that means x is going to equal what? Huh?
-3.
-3, exactly. -3. Did you check your answer? Yeah, plug that -3 back into your original equation, solve. Okay. And it does work. I just popped it in my calculator, make sure it works. Let's do a harder looking one, because people hate variables. Anybody know what that E stands for? You're gonna learn it in 6-3. I just don't know if you've ever been introduced to it before. If you did my extra credit in intermediate algebra, you've seen it. Okay. If you didn't, totally okay. I get it. Okay. E is not a variable. Okay. That's called Euler's number. Okay. Spelled Euler, but it's German, so it's Euler or Austrian, something like that. And you're going to learn all about Euler's number in this, because now you're learning about it. So it is an actual, it's like pi. Okay, there's a specific number that is associated with that. But notice what we have here. We have one that we need to simplify. So let me kind of work this one out with you. First off, looking at the left-hand side, do I need to simplify anything? All I need to do is do what? Let's multiply the powers. Can we all agree with that? Just multiply x plus 5 times 4. Are you good with that part? So let's rewrite that. We're going to have this e to the 4x plus 20 is all equal to, now here's where you got to be careful. You have e to the x sitting outside, but remember algebraically, one, you have e to the x times e to the 8x, or you can rewrite this as e to the x all over e to the 8x. But what happens right here? Don't forget, what do you do when you have the same base? Go back to time, same base. I never said same variable, I said same base. Same base, what do you do with powers? Subtract them. Come in here and go, okay, well, up here to simplify this, I have x minus 8x. Isn't that what you've done every single time when you have these x's? Yeah, it's just on top you have 1x, on the bottom you have 8x. So subtract them and you're going to get negative 7x. And so therefore, when you do that, notice and you rewrite this whole thing, you've got e to the 4x plus 20 is equal to e to the negative 7x. And then the math is the same, right? Aren't we just going to come in here immediately and go 4x plus 20 is equal to negative 7x. You are not dealing with a quadratic, which just means you just got to get what? Isolate the variable, right? Get x by itself. I don't care how you do it. Okay. Subtract 4x from both sides. You get 20 is equal to negative 11x. Divide off negative 11. And I get x is equal to negative 20 over 11. And that, ladies and gentlemen, is your answer. And I will be honest, you can put all that in your calculator. Every last bit of it into your calculator that way. Matter of fact, whenever you hit your exponent button, just make sure that you hit your fraction button and it will allow you to put that negative e in there. When you do this, if you decide to check your answer, you end up getting, I rounded, 336,809.4864 is equal to 336,809.4864. So that tells me what? Did I do the right math? Yeah, there you go. I know it was correct. If I can help you now in math, don't be afraid of ugly. Okay? That thing looks ugly. But that's actually why you went through intermediate algebra. Okay? If you really think about it, we've had some ugly problems in college algebra, right? We've had some ugly. But really, let's really compare the ugliness compared to what you probably saw in intermediate. They're not the same. You know, some of the stuff you saw in intermediate was like, holy crap, what do they want me to do? It was just a crap ton of simplification, wasn't it? That's why. That thing started ugly. It's still not great, but it looks a lot better once you go in there and start simplifying a little bit. Okay, simplify, and then use your calculator, plug everything in. Okay, see if that works. Last one, and then we're going to jump into 6-2 and call it a day after that. I want you to do this one. You get the twos. Sometimes the hardest part is finding the stupid bases sometimes. Okay. When you put that back in, if you'll notice very carefully, you don't have to do a lot of checking, because look, if I put a 4 back in, what's gonna happen to that first term? It should go to a what? 4 minus 4 is, anything raised to the power of 0 is always gonna be a, well, I don't care what it looks like, I don't care what's happening inside that parenthesis, everything raised to the power of 0 is a 1. So this one, plug in a 4, I get negative 4 plus 4, what's that gonna turn into? 0, which is gonna make that a, so does 1 equal 1? You got the right answer. I say this because if you run into one of these questions on your final, can you check it? So you can actually leave the test going, I know I got that right, or I hope I got that right. That kind of makes sense there on that one? Okay, check it. It takes 2 seconds to check. Okay. Oh, we have any issues? Good. Hardest part probably, what do you think? Maybe finding the bases? Was that a little bit hard? Okay, play with it. Okay, that just because it doesn't, I'm not gonna say it comes second nature, it doesn't, okay? Because you don't think that way a lot. Okay, especially because you're used to thinking of squares, like, hey, 2 times 2, you've got 2 squared. But when you're having to think of like 2 to the 5th and all that other stuff, it gets a little harder to figure that out, okay? That one, how many of y'all got fooled by the 4 and started trying to do like 4 squared and all that stuff real quick? Start that, yeah, all of a sudden that didn't work out very, let's be honest, at 4 squared, you're like 16, 4 cubed was not 32. So how many of y'all want it to be 32? Did you put 4 cubed in by accident? Did you? I've done it. I did it yesterday whenever I was doing some of the notes. I was like, you knew better. It happens. Okay, and that's when I realized, okay, 4 is probably not a number that I need to be looking for. Maybe I need to go lower. Okay, but it does prove the point. Exponentials grow exponentially fast. That's what they're called, exponents. Okay, they grow really, really fast. Okay, so knowing that, let's jump into 6-2. Every single one of these questions I'm about to show you, this is called exponential modeling. These are all word problems. Okay, 6-2 is literally word problems. We're going to go through, we're going to start working on 6-2. I do believe when making your notes, I'm not saying I picked out the easiest ones in your homework, but I did try to make sure that these are going to be the ones you are going to see on your final. Okay, so you could possibly see one of these on your final. Okay, I have not put out the final paper yet. I'll do that on Friday, by the way. I mean, there's a review there you can start looking at, but I'm doing some double checking since they rewrote the final last semester. Remember, we had that one that wasn't on your deal. I don't want that to happen again. So I'm just making sure to go double check. And then what I'll have happen is my wife will double check it for me. Because, after you look at something so long, everything looks the same. We're making sure the final jobs with the everything else. Okay. And then I'll go on there and start listing where you can find it all. And then, of course, next Monday and Tuesday, we'll go through some review questions. Okay. So jumping into 6-2. Exponential models. This first one here is called models of population growth. Okay? Exponentials are really good about modeling things in the real world. Yes, there's a little bit of some nuance as you get up higher, but these things do work out really, really well. Notice this one right here. They give you a little equation here at the bottom. I'm going to write it up a little bit here, a little bit bigger. Population growth is P of T, P sub 0, A of T. P of T being a function, right? Makes sense. And this is going to be the number of the population after a given time. Right here, initial population. Now, of course, the T is going to stand for time. The A, okay, that is going to be called your growth rate, okay? If A is greater than 1, you have a population increase. If A is less than 1, don't say you have a population decrease, you actually have a population decay. If you look at birth rates, mind you, the formula is a little bit more extensive, but birth rates of some countries to replace a population, okay, you need a certain base number. I forget exactly what that number is. It's to replace, like, basically a mom and a dad, they have a baby, okay? And then that kid grows up, has another baby. That's not enough kids. Why is that? Because 2 people are making how many humans? 1 human. You keep that going, you're going to have problems later on down the road, okay? So to keep a constant, you would want at least 2 people having 2 kids. They're noticing in China right now that their population is dwindling fast, okay? 1, okay, now mind you, I haven't done exactly some extensive checking on this. From what I understand, for a long time there, they had 1, you can only have so many children. 2, who's preferential? Males. Too many males creates too few females, and this biologically does not work when you're trying to create another female or another male, okay? You've got to find some way to create these things, and it's just not happening. So the population is in population decay. There's not going to be enough people later on to take care of the other population that's sitting there, because that's what's happening right now. I'm working, you're working, we're all working to take care of who? The people who are retired right now. The Social Security you're paying, your job is going to pay for them. And one of these days, children here, they're working, are going to pay for you if there's enough population. That's the problem. Okay, so a culture in decay is why you get that. So notice initial population. Initial population, it's at time 0. Right? Because that's where, hey, remember what my exponential is? It always equals what there? 1. But this is where I'm starting my intercept, okay? Is at that point right there. So let's look at an example here. A certain species of fish is to be introduced into a lake, and experts estimate the population will grow, and they give you the formula. P of T is equal to, that's 771. What is that? I literally just gave it to you in your formula. What is that number right now? That's my initial population. Let's say that's how many fish I got in a barrel, and I go dump those into the lake. That's my initial population. My growth rate is a 4. And where t represents the number of years from the time of introduction. What is the quadrupling time for this amount of fish? Well, my initial population is what? 771, right? I want to know how long it's going to take for those fish to quadruple, which means I'm going to multiply it by what? 4, exactly. I'm going to take that 771 and I'm going to multiply it by 4. I want to know how long it's going to take. Well, let's do this. When you do the math of this and you do 771 times 4, you end up getting 3,084. I want to know how long it is before I have 3,000 some odd fish. Well, can we all agree that eventually that's going to be where the P of T is? But I don't know how many years yet. I've got to solve for this. Well, that's easy enough. Watch what I'm going to do. Let's set the equation equal to that number. Because that's what I want it to be equal to eventually, right? I eventually want to see when is this, the whole equation, going to equal that number? After how many years? Well, notice here I have my 771. I have my 4, and then I also have this T of 3. Well, let's just do some algebra. Let's divide off the 771. And what are we going to get? Should get a 4. So I'll get 4 is equal to 4 T over 3. How about you divide off the 4? 4 divided by 4 is just 1, isn't it? 1 is equal, what's left over here? T over 3. Multiply that 3 up. T is going to equal 3 years. How do I know that's going to work? Well, let's look at it this way. If I plug T into 3, 3 divided by 3 is just 1. 4 to the power of 1 is just what? 4. 4 times 771 does give me my 384. Can I help you out with that one? So notice, by knowing this value, I can go, hey, I know that in 3 years after this initial dump, that's how many fish I'm going to have. I say no, more or less. You'd be surprised how accurate some of these are. Okay? Especially once they find out the growth rate of something. Knowing that's how that one is done, how would you do the second one then? How long will it take for the population to reach 12,336 fish? Where would I put that? Left-hand side? Right-hand side? What am I going to do? Left, because I want to know when after all of this. Notice this, that's asking you the question. It's saying, how long? I don't know. That's why I'm solving for T. Okay? How long is it going to take for that number to get there? Well, that's what we just did. So we're going to come in here and write is equal to 771 4 T cubed. Do the math. Same thing, right? As you're working this out, and then I'll finish it, keep working. Just realize when it's saying how long something is, that means you don't know the T value. So they're giving you this number saying how long till this number gets to there. Realize in the last one, if I'd have put in that P of 3, it would end up equaling 3,084. That's how come I put the 3,084 on that side of the equation. Okay. Coming here, once again, I'm going to divide off that 771. End up getting 16 is equal to 4 T over 3. Divide by 4. I get 4 is equal to T over 3. Cross multiply, that means multiply that 3 up, and you get T is equal to how many years?
12.
There you go, 12 years. Notice this one. In an effort to control vegetation overgrowth, 139 rabbits were released in an isolated area free of predators. After 2 years, okay, it is estimated that the rabbit population has increased to 556. Assuming exponential population growth, what will the population be after another 6 months? And you got to watch out for this one. Okay, first off, I'm giving you another population one, okay? And you want a little hint, all of these equations are the same, they're just changing the variable line, okay? We're only using really one formula, okay? Notice we're gonna deal with population again, we're gonna deal with P of T. Initial population, and I'm gonna have an A and all that to a certain amount of time. Realize, do you have an initial? You do, don't you? What is it? Very good. My initial is going to be 139. They also give me something else. What else do they also give you? Don't they give me the P of T? What is it?
556.
556 after how long? So realize I do have a T right now. It's equal to 2. My P of T after 2 years would be the 556. So we can just say arbitrarily this P of T with 2. So actually, if we want to be correct here, P of 2 would equal 556. Notice what we don't have. See an A value anywhere? It's your growth rate. Well, that's okay, because watch what we can do here. I know that after 2 years, I'm going to have 556 rabbits, right? I also know my initial amount was 139. I do not know my A value, but I do know what? That's after 2 years. So let's just go ahead and come in here very carefully and start solving. Let's come in here and divide off this 139. $556 divided by 139 gives me a 4. 4 is equal to A squared. How do I get rid of that A squared? Square root it. But hey, you don't need the negative. Remember when you square root, you always do plus or minus. On this one, we only need what? The positive side. Take the square root of both sides. I'm going to get what? A is equal to 2. Now, can we all agree now that I have a full-fledged formula to model the population? Because let's look at it. I have P of T right over here is equal to my initial. That's 139. I now have an A value of 2. And then we have T. Because now my independent variable T, I can start plugging in and get in the growth. But then it says what? Assuming exponential population growth, what will be the population after another 6 months? 6 months from where? The initial? When?
After 2 years.
2 years. So what needs to be my T? If 2 years is a 2, 2.5 would be what? There you go, 2.5 or 2.5. That's the number you're going to plug in. 2.5 or whatever number they decide to give you. If they say 3 months, then there you go. Figure it out there. 2 1/4, 2.25, right? But still for this, we're going to do P of 2.5 is equal to 139 to 2.5. Looks like you're going to get out a calculator. Round, please read your questions to the nearest rabbit. You can't have a partial rabbit. Okay. When you do that, you're going to end up getting 786 rabbits. That's a lot of rabbits. just in 2 years, when you only started out with 139. And that's actually pretty close because rabbits do grow fast. Okay. Anybody that hunts knows this. Like any year that we have a bad drought, okay, where like maybe the larger predators like go away, or for a while there, they weren't allowing you to hunt coyotes for a long time. Well, look what happened to the rabbit population. Okay. The rabbit population went down. But whenever you were able to hunt coyotes and stuff like that, and you had to have a license, you just go out there, people were killing them like crazy. Well, what happened to the rabbit population? The rabbits were like, oh, it's a wild night. And then they produce fast. Okay. Good on these? You might get one. Okay. Look at no. What type of function does this be? Increasing or decreasing? Decreasing, exactly. It's going down. Okay, look at where it's going. The other one was increasing, wasn't it? Because what's happening to our population? It's going up. Okay. Should you have the population decay? Yes, you're not going to be having that. You're okay. Your populations are having a very good sex life. Okay, they are doing A-okay. Okay, radioactive decay. This one always threw me. The math, not so much, but what it was saying. Literally, once again, though, let me show you. Notice it's almost exactly the same formula. We're just using some different variables. What it is, I have so much of a certain substance. This substance is radioactive. Don't get hung up. Everything's radioactive, even a banana. It just depends on what type of radioactivity we have. Okay, there's like 3 different types. It's a safe radioactivity. Like your phone, I'm sure. Your phones aren't that bad. Now you have A of T. And then you have A sub 0 A T. Once again, it's an amount after a certain time. Here's your initial. Here's your time. And here's your growth rate. The growth rate for radioactive decay, now hear me out, will always be between 0 and 1. Why is that? Think about it. Look at the wording. Remember the graph I showed you? Very first thing we started looking at exponentials. What happened whenever you were between 0 and 1? What type of graph did you have? The decay. So to have decay, it's got to be between 0 and 1. Okay? So 0 and 1. That's where x will be. You don't see this as 0 is less than that. I've only got one question. And actually, the harder part about this question is actually, once again, the hardest part about this question is going to be your initial. Step 2 and step 3, easy breezy. Okay? Notice what this is saying is I have a certain amount. Let's look at the question. It's got 3 parts to it. The half-life. I'll explain that shortly. Anybody know what half-life is? You heard of that? You may have heard. Have you ever heard of it? You heard of it? Do you know what it is? Sort of. Okay. The half-life of radium-225 is approximately 14.9 days. Okay. Determine A. Okay. We're looking for A. That's our growth rate, right? Except for us, it's going to be decay. Determine A, so that A of T equals A naught. A of T describes the amount of radium left after T days, where you have the initial amount at time 0. And then you're going to need to round to 6 decimal places, which means go to 7, round to 6. Okay, so if you start getting a bunch of red bars, that means you're going to 6 and round to 5. Go to 7, round to 6. Okay. Look at this one very carefully. To figure out A, this is what we're going to do. You're going to need your calculator for this. Half-life means after so long, I have an initial amount, right? Here's my initial amount, my A of 0. Half-life means I'm going to have that amount. half that, right? After how long? What's it say? 14.9 days. I have half that amount. I'm saying that wrong for a reason. I'll explain it here shortly. Okay. So notice how I'm going to write this formula. I'm looking for A right now. Am I not? Look at how I'm going to write this. I have A of 0. I'm writing the right-hand side, by the way. And then I have A of 14.9. I know for a fact, I don't know my A yet, do I? But I do know if I plug all that stuff in, I should have how much left of my initial. What's the terminology used to be? Half-life, right? I should have half of that, right? So shouldn't I just divide that by 2? Start solving. First off, let's get rid of that A0. Okay, well, to do that, let's look at this very carefully. Can't I just multiply by 1 over A to 0, 1 over? That's just going to reduce all that out, isn't it? And that's gone. We're going to be left with A to the 14.9 is equal to 1/2. Hey, how would I get rid of that exponent of 14.9? Don't lose me now. Come on, y'all did it all. If that was a square, what would I do? Take the square root, right? Who says you can't have decimals in your index? Why can't I take the 14.9 through? You have a calculator. So that's exactly what you would be doing right now, is you would take the square, you would take the, if I wrote this out mathematically, I would take the 14.9 here and come over here and do 14.9 for my index there. And that's going to leave me with A is equal to, and then notice you get a really ugly decimal, okay, of 0.954546. And actually what you get, just so you know how to round this, because I don't want people to get messed up on this, this is what you get. You get 0.9545455 ... But I'm only rounding to here, right? Which means I need to look at this guy to decide what to do to that guy there. Okay, remember, you go to 7, around back to 6. For those of you going to take statistics, that's a very important lesson. Notice you just found your A value. That's your growth rate. I say growth. That's your decay rate. Because we're less than 1, aren't we? Well, notice what's going to happen here. Now, literally, if you got that, you're literally just going to be plugging in things. It's going to say, hey, you have 15 grams of this radium-225 sitting in your hand right now. Okay, here it is, 15 grams of it. Okay, after 5 days, how much radium-225 do you have? Well, wouldn't I just come in here and go, okay, well, how about A of 5 is equal to, well, my initial amount is how much? Isn't it 15 grams? I have that really ugly A number, okay, which is going to be my 0.954546, all raised to what? The power of 5. All that's going to go into my calculator, because why would I do any of that by my head? And I would say this, that after that many days, I have 11.887 grams. So really the hardest part about this problem is figuring out what? Your A, right? So notice you can do, it does the same thing on step 3. And as long as you get the proper A number, you're good. Now, once again, you've got this A, but now they're saying after 9 days. Once again, I still have that initial 15, and I've still got my same A, but now I'm going to 9 very quickly on the math here, and I get 9.869 grams. Okay. We'll finish up the other, but hear me out before you leave. Don't leave yet. Mathematically, I've taught you the math. But I don't like people leaving and thinking they understand something. We call this the Dunning-Kruger effect. Anybody ever heard of the Dunning-Kruger effect? You ever tried to learn something and initially you learn like, you're like, man, this is pretty easy, kind of like you learn a lot really, really quick, right? And all of a sudden you're really smart with it. You think. Okay, that's the Dunning-Kruger effect. And actually it looks like this. It's a graph that looks like this. It comes up where you learn, and then you realize, uh-oh, then all of a sudden it drops off. Okay? And then it kind of comes back up here and it peters out and go. That's what most people get to hear. And then guess what? They quit. Because what happens? It actually gets a lot harder after that. Most people peek here and think they know everything. Okay? You can figure those people out by somebody who's made it over here. Because they'll start asking this person questions. They're like, you have no idea what you're talking about. I don't want you to do that with half-life. What this half-life is not saying is this. It's not saying that I go over here and let's pretend that this is something that's radioactive and every 15 days it goes down by half. It is not shrinking in your hands. Okay? Is that what some of y'all thought that was happening right now? Because the grams were going lighter and lighter and lighter? Okay? What's happening is this, is I have this element in my hands. After 5 days, instead of having 15 grams, I only have 11.887 grams of radium-225 in my hand. I still have 3 and some odd other grams of something else. What happens in a half-life is it loses either protons or electrons and it changes into a different element. Okay, so this one will actually change elements. After so long, after so many days, you could find out how many days until you have no, right? All you gotta do is make that other side equal to 15, right? You can say, hey, after so many days, I no longer have radium-225. And you can look it up, Google it. It's called acetine or something like that. I forget exactly. 222. It's a brand new element you're holding in your hand after that many days. Still 15 grams. It's changing over time. Okay, that's what they're saying. Like uranium has a half-life. Okay, so like if you have like a pound of uranium, its half-life is like 5,375 years. So that means if you found some uranium, you can actually go back and date it and go, well, this thing is how much this thing used to weigh. If that's how much uranium's in it, they can go backwards. That's how they do the carbon dating. When they say how old something is, carbon dating is, I think, no, I'm lying to you. Carbon is the 5,300 some odd. Uranium's got tens of thousands of years, which is why they say if they ever blast a nuclear bomb, this place is desolate for the next 10,000 years because it's going to stay radioactive after all its half-lives go away. Okay. That's what half-life means. You still have the same amount, more or less, but it's changing to a new element. Okay. Don't think that it's shrinking in your hands. Okay. Or that just proves it's gone. Tomorrow we'll finish up with a very important one that you're going to like if you like money. Okay. And then we'll jump into 6-3 tomorrow. Okay. Did y'all do?